Fantastic. Thanks, everybody, and appreciate the double good morning requirement. Spooky action at a distance. Who knows what that's actually from? What you got? What's that? Quantum mechanics, right. Who said it? Einstein. Yeah, good. Fantastic. Okay, we're definitely not doing quantum mechanics, but I do like the quote. Oh, no. And clicker dead. Here we go. Does it work now? It does. Okay, disclaimer. Read it real quick. Good job. Okay, traditional C2 concerns. What we actually are going to be talking about is how malware and or bad actors communicate over the network. And the reason we're going to talk about it is because we're going to go through like a crawl, walk, run phase, and then you in the white shirt, what's your favorite sports car? Bugatti, good job. Okay, so, and then we're gonna get in a Bugatti and just take off at the end real quick, okay? So I promise we're gonna start talking about packets for a little bit and ransomware, and it's gonna seem like it's basic and just accelerate quickly, just trying to get everybody on the same page. So for ransomware, for malware to work like ransomware, they have to send you like a phishing email or get in through some sort of CVE, and then they install some stuff on your computer and it communicates out to a server. That's C2. So that's what C2 is. It's communicating out to a server. The little dots, that's going to be the network, right? So whether that's in a cloud instance or whatever it may be, that's your network layer there. Okay. And then they have to communicate back out to a bunch of different servers to be able to accomplish ransom. That protection. So when we talk about things like malware talking out, we should be able to see it there at all times, okay? That's the deal. So that's what we're going to be talking about. And at that area in your network, we normally have some sort of firewall. And they maybe even have AI, and maybe even have been saying that they have AI for like 10 years, right? And when I talk about firewall now, that sounds pretty antiquated, but really we're talking about anything, whether it be an on-prem tool that intercepts traffic and then creates rules about what traffic is allowed in or out and it potentially does inspection. Or it can be in GCP, Azure, AWS, security groups. It can be a firewall on the device. It can be a firewall at layer 3. It can be a firewall at the WAF, like at the web application firewall. Any of these things that control traffic in or out are things that can impede the ability for malware to communicate out to its makers, okay? And that makes it hard. And so for applications, there's things like web application firewalls. Deep packet inspection looks at the application layer of that traffic to see if there's anything weird in there. That's what it's doing. Threat correlation, encryption, proxy inspection. When we look at network detections, that's completely separate from firewalls, right? That's like shipping out the data to things like Corelight and Splunk and Darktrace, ExtraHop, Cisco Firepower, all of that stuff. All of that is designed to be able to identify the malware communication, let you know it's happening, and or stop it. All right, but it keeps happening, obviously, so what's that all about? And where we're going to focus here is what I'm calling detection cross-section, right? And when we look at detection cross-section, that's actually another physics term. I thought I made it up, and then I Googled it yesterday, and I was highly disappointed. But applied to the OSI layer, which I promise this is not an OSI layer talk, no one needs that, right? But when we apply it to the OSI layer, at any given point in the way a packet's built, you're creating a cross-section for detection, right? So if I'm creating malware, which is what we're going to get to at the end in the Bugatti, if I'm creating malware that I want it to communicate, how it communicates, I have to build packets to communicate back out to me. I'll use common protocols usually. That's what we usually do now, right? And at each point that I add pieces to that packet, it's more cross-sections, more stuff that can get detected by any of those tools that we just talked about, right? Okay. So at layer 2, Ethernet layer, we're not getting anywhere. We're not routing, okay? This is how I always think about it. Layer 2 is MAC addresses. And at layer 2, we're stuck in here. Hold on. Yeah, there we go. We're stuck in here. I knew that. That's why I never do animations. It just always throws you off, you know? So we're stuck in here. We're stuck inside that little dotted blue line. That's what we're talking about. And normally we're going through something that's called a switch. And we have like a CAM table inside the switch that has MAC addresses that says this MAC goes to this port, right? So when I build a packet, I want to communicate where that solid blue line is. I actually don't need anything more than just the Ethernet layer to be able to get that packet from one machine to another machine. So it never goes through this area where we have a firewall. It does have there's a local firewall option, but usually local firewalls aren't concerned with layer 2 either, right? Because what a weird thing to build a packet without an IP on it. That doesn't make sense. That's the whole point of why we do stuff. All right, so we'll talk about that. Great, and this is what that Ethernet frame looks like. There's not a lot of cross-section in here for detection. There's also not a lot of area where we can have data. We can shove some data in here, but it's pretty visible, right? And it looks weird. If you just had like an Ethernet packet that was giant and it had like no other stuff inside it, that'd be weird. It'd be something that'd be easy to detect. It'd be anomalous. All right. And normally, when we're at layer 2, when we're bad guys or red teamers or malware creators, when they're trying to communicate internally, we'll use things like SMB named pipe, raw TCP, stuff that we already know about. HTTP, HTTPS can be fine, but that's kind of weird for machines to do to each other in general. But you know, if you have stuff that communicates, that's attempting to do security like endpoint devices, they actually do a lot of communication between each other as well, right? So, okay. This is stuff that we normally use, and there's all kinds of detections that can be done. Because if you decide to use a port at a point where you didn't need to use a port to communicate, you've increased your cross-section of detection by adding IPs and adding ports, right? And so there's stuff that can be detected there by all those devices. Awesome. Layer 3. Now, that malware wants to communicate out, something outside. It requires a route. So we have to give it an IP address, okay? What else do we need to be able to communicate out? Potentially. It was honestly a trick question, so I'm glad no one answered. Nothing. We need nothing else to communicate out. Usually someone's going to be like, we need ports. I'm like, nope, you don't need ports. All you need is the IP. It'll get there, and you can communicate. All right. So all you need is IP address. Right. And as we route that out, I can now route out anywhere I want in the world, theoretically, or internally, to get to my malware server. That's what I want to do. But I don't need anything else. And there's a lot more cross-section here, so fine. But like, you have to have this stuff to be able to route anywhere. So that's a required cross-section for communication. But again, any data just sitting on top of here, this is where the other protocols would normally go, right? So that's inspectable. Great. So all these are detections. All these things can be detected on or blocked. And so at layer 3, when we're not using a port, a lot of the ways you'll see ICMP-C2, you'll see IP discovery, ARP discovery, like enumeration, that kind of stuff. That's where we're kind of stuck at layer 3 as red teamers or threat actors. Layer 4, and we'll quickly get through this. Now we need ports and protocols to be able to communicate. So layer 4, we're going to give it a port, and now we can detect and or block on ports as well. And this is where we commonly block at firewalls, right? If you know an IP and you block it, that's great. A bad guy's just going to change the IP, so it's not really highly effective. But if you're doing effective like network segmentation, like what did they say? Like my big takeaway yesterday was like segmentation is hard. Was anybody there for that? That was great. I was like, yes, that's good. It's a syscontrol for 20 years, but it is hard. I got you. Okay, so segmentation. That's where you can apply things to block ports. And there's when we get to detections, there's like port protocol matches that can trigger things to be anomalous, right? So if it's port 80 and it's not HTTP, that can be weird. And there's a lot more stuff that we can detect on, but specifically focused on the ports, but also you can get and start doing TCP options. So there's ways, if you've ever gone to some of the SANS classes, some of the instructors there will talk about how they help develop ways to sneak data out of countries that's really hard to get data out of by shoving the data into the TCP options, right? So that's another way to do kind of covert communication. Awesome. Layer 5, 6. Now we get the deep packet inspection, DPI. That's been going on for a really long time, but it's where it's looking at, is there weird stuff going on inside the data section of the traffic? And that's HTTP or whatever it may be. It's where we can see payloads, it's where we can see attacks, it's where we can see executables going across the internet. Wherever it may be, that's where that inspection's happening. And it will get caught, right? Including any of the headers, any of this stuff is just like, now we're like really blowing up on all the stuff that we can detect on. It's a massive amount of stuff, right? SSL, when we add on encryption, we now have a certificate, and anything in that certificate can be used for detections as well, right? And correlations and identifying stuff going on in the network. Right? So there's a lot of stuff there. Now we've blown up. Too much stuff, right? And so we now have IP address, port, sending port, header options, and in an application we can detect on URLs. We can use JA3 hashes, which was a Salesforce way to look at unique TLS encryption done by different packages of executables, so you can identify the executable communicating based on the SSL negotiation, right? Certain anomalies, encryption versions, payload data, user agent, so many things. There's so many ways to get detected, so many ways to get caught. And to be completely honest, most malware communicates at this layer, right? And so that's why we have so many things that work to detect stuff at this layer. So what's a hacker going to do, right? And if I didn't have a bunch of randomly generated images, it wouldn't be the conference it is today, is it? So it makes it good. Well, so we're going to use something called QuantumCat. That's why it's spooky action at a distance. Again, really has nothing to do with quantum physics at all, but let's get set up. So the first thing you do with QuantumCat is you're going to identify egress opportunities. So in your environment, whether it be a cloud space or whatever it may be, you need to identify how can I actually get through whatever that firewall device or acting firewall device actually is. And when I do that, I want to be able to reduce my cross-section of detection as much as possible. I also want to have a bunch of options, right? So right now, what's the best kind of go-to C2 communication right now? Anybody? Anybody? I don't want to call anybody. What do you think the most common C2 communication is right now for malware? Command and control. Yep. DNS is yeah, pretty popular, right? And it's hard to block. Easy to detect though, right? Because it's not encrypted. So if you just look, you find it usually. Awesome. Okay, what's the other one? HTTPS. There you go, HTTPS. Why? Because it looks like web traffic. And it's generally encrypted. So unless you're doing a encryption, unless you're proxying the certificate encryption of your web traffic for all of your users, you can't actually see inside of it, right? But we still have a lot of cross-section for detection there. And what happens when I go over port like, I don't know, if your firewall has port 555 open and then I use HTTPS, is that weird? Yeah, it's weird, because it's supposed to be on what port? 443. Yeah, it should be on 443. And if it's not, now it's a detection. Okay, so I don't have a lot of options. I can only use port 443, TCP, HTTPS. That's my primary way to communicate right now. And I have all these ways that things can be detected. That sucks. Now, with QuantumCat, instead, all right. Did it go black? I just blue screened of death. I'm not kidding. Isn't that amazing? Yeah, there we go. Thank you so much. Okay, so I'll talk through some stuff. It's fine. We're going to be fine. Don't worry about it. Okay, so with QuantumCat, the idea is we're going to set up and we're going to create a carrier wave or a sine wave, and then we're going to modulate that sine wave to transmit information. That's commonly how just RF works, like radio frequencies, right? And what are the three common ways to modulate a sine wave? It's cool. That's what you're here for. That's fine. It's amplitude modulation, frequency modulation, phase modulation. Okay? There's lots of other things you can do, but that is what we're going to do with packets. And instead of being worried about increasing our cross-section of detection, we can use any packet we want, any layer we want, as long as it can get where it's supposed to go, any port we want, and we don't increase, and none of the data we're transmitting is going to go inside of the packets. So there's nothing to be detected on. We're going to do that by sending packets at different speeds, sending packets that then also change the amount of random bytes in them, right? And you can do it by 1 byte, and that still creates a 0 and a 1, okay? And we're going to do it by changing phase modulation, which actually ended up kind of sucking because it just looks like frequency modulation because you're just changing the phase of where the peak is of the sine wave. It really just looks like frequency modulation. So instead of doing that, we're actually going to alternate ports to signify zeros and ones for the phase. And that does a couple different things. But one of the really cool things it does when we're worried about those detections is and you're going to see all of my pop-ups here. This is great. Really, really poor. My Discord's going to pop up. We've got all kinds of stuff happening. Okay. It actually breaks the way that you inspect sessions. So all of those tools and we'll have a slide pop up at some point if I can get back to slides. We're almost there. Cool. Every single one of those tools we talked about is pretty much based on Suricata, Snort, or Zeek. Okay? Zeek used to be called Bro. So every single tool that does network inspection or NSM, including the EDRs that also do network inspection, every single one of those is based off, like, your Palo Alto firewall. If you go log into it with SSH and then like search for Snort, you'll find SnortConf because it's just Snort. Okay? All of them are based on that, and every single one of them is concerned with doing session detection because that's where you can find the different anomalies. And we're back. And we're back. There we go. Okay. Because that's where you can find the anomalies. When I'm looking at a session, I can say, hey, like this is a communication. TCP sessions are a little bit easier because you're like, oh, there's like bidirectional communication here. UDP sessions, you have to like have some math to figure out, like, is this still the same session? Is it a different session? But generally, if it's an IP5 tuple, so it's like IP port protocol, right? Then you can say, hey, this is a session within a given time. And all of them do inspection on those sessions, but if you swap ports back and forth, it breaks the session inspection because there's separate sessions every time, right? And so now it can't do those detections either. Great, so we're gonna hop in to what that looks like. And by the way, when we go through it, I'll try to make up a little time here. When we go through it, raw Ethernet just looks like raw Ethernet, right? So this is live view of what it'll look like when we actually send it over the network. I just don't want to have to also show you Wireshark while we do it. So I'm going to show you these real quick too, right? So this is Ethernet communication, raw IP. You can see there's like nothing here, right? That's the idea. There's barely anything to detect on. It's the smallest cross-section of detection possible. ICMP, same thing. There's nothing there. And you can make it different codes. If you want to do phase modulation with ICMP, you can make it different codes or types. And that could be how you modulate instead. The world's your oyster, right? UDP, awesome. And that breaks all those detections. So first thing I'm going to do is select modulation. And I love this. I've seen this a lot in presentations here. And I'm just really happy about it because it validated that I was absolutely going to leave stuff that was missing AI up here, right? Everybody's doing it. It's fine. Cool. And we're going to start with frequency modulation. So we're going to modulate the speed at which the packets move. And we're not going to blue screen because that would suck right now. Okay. Yeah, sure. I can do it like this. Why not? No, I can't. I can't do it. I'm sorry, guys. Here, we're going to change the way. Control-Shift-P. Duplicate. Fantastic. All right, live demo time. Ready? High risk. Frequency modulation. So basically, we're going to use some Python in Jupyter Notebooks. And you can go download this from GitHub right now if you want. And I'll add to it because this has been really, really fun to do. And so I'll add to it as we go. But this is kind of what that sine wave would kind of look like. We actually get to do it a lot more simply in that we can have really, really defined peaks and valleys. We can really define that so it looks more like it's already gone through a fast Fourier transform. And you'll see that here in a bit. We can generate a packet with Scapy, so we're going to be using the Scapy library most of the time. And then when we do that, we can set the frequencies to 1 hertz and 2 hertz, representing 0 and 1, right? And it'll kind of look like this. This is what it's going to look like if you had like graphed it on the other side, which we will. So normally, I got some stuff in here for you to list your interfaces so you can identify what interface you're going to go over. You can set this, so like how do you know, especially with on layer 2, there's a lot of broadcast noise with MAC addresses, right? So you want to restrict it to the MAC address that you expect it to be coming from, right? That's how this is done. And so here we can go ahead and start listening. So it's listening for those packets. And we're going to go ahead and use Ethernet send and send the packets. And there it is receiving them, right? And it's really simple. Everything I just said sounded really complicated, but it's just 1 second, 0.5 seconds, 1 second, 0.5 seconds. And then you look at the difference in the time that those are translated on the other side, that equals 0 or 1, 0 or 1. And you can change those frequencies to be whatever you want them to be. You can put jitter into it. So you can like add jitter into the frequencies so it doesn't look clean, right? And you can transmit information that way. And so now I transmitted the word cat over Ethernet with 0 data inside any of the packets, right? But I could also transfer commands. I can do ls and look for Etsy password, right? Or cat Etsy password. Except normally, that'd be like immediately detected because it would show up inside the packet, right? And then I have to be worried about encrypting it on both sides, and it's like a lot of heavy weight. Nothing. There's absolutely nothing inside the packet. There's zero way to detect it. Yeah, you're welcome, vendors. There you go. Okay, so we can do just IP, which I didn't actually test this one on the other side, but probably make up some time. We got the IP capture. Let's see if this one works. See if I have to configure this. Oh yeah, it likes to do that the first time. I promise you can restart it, and then it'll start receiving the packets. All right, it didn't receive the first packet, so stop doing that. You're so mean. All right, we're gonna skip IP. It's been a jerk lately, but it does work. Promise. We're receiving only some of the packets, but you'll see the 0 and 1s on the other side. Frequency modulation is fine, but there's a certain threshold that you have to worry about, right? Like I need to be able to get a clean wave on the other side, and so I can only go so fast. But just to show you this going over the internet here, let's see, ICMP, which one did I do for this? Did I do UDP? I did. All right, ready? We're going to go ahead. I have something, a VM set up in US West 2, and we're going to use UDP to do frequency modulation over about 30 hops, right? So that was the next thing. I just wanted to be able to show you, hey, this looks great local when it's on your device, sure. But of course it crashed, so just give me a second. But the really interesting thing, and what I was worried about when I was doing this, is I thought that I have to be concerned about the way that the wave would change as it routed through different latencies, right? And so my original hypothesis was that I would have to treat it like it was a mechanical wave and do a lot of filtering on the other side to get it back to a nice clean sine wave. As it turns out, as long as the latency, doesn't matter how many hops it is, it can be around the world, as long as the latency is consistent, or reasonably consistent, you can just put tolerance in on the other side, and the receiving side doesn't care. It looks like it's arriving at whatever speed it's arriving at, and the frequency actually maintains. So I didn't have to do any of that, and now we're going to go ahead and just do this live. Cool. So pretty fast too, right? So it'll receive this information. I'm sending it from here. I'm going over UDP port 443. What uses UDP port 443? I'll just drop in some nuggets real quick as we do this. It's QUIC. QUIC. Yeah, and DNS can do it too, depending on it. So QUIC, if you ever browse to Google while you're also using Wireshark, you'll see a lot of QUIC on Wireshark. And it's because that is it's about half of the internet uses QUIC now for browsing. That's the packet that's underlying your browsing. Okay, it's a UDP packet, not a TCP packet, and most stuff, heads up, all of the vendors really struggle to detect anything on it because they don't have a lot of protocol signatures written for it. So just so you know, that's a concern. And here we go, we can just cat over 30 hops to US West 2, okay? So we can do this out of RSA's network, so we'll have to go stop by the SOC and see if they see anything like that. While we're talking about it though, just another little nugget, when I did it from source port 53, and this is important stuff to remember when you're just doing this kind of base rules of C2 communication, when I do it from source port 53, it didn't matter what I did, Azure blocked it. I don't know why. Yeah, interesting note. Probably doesn't like it because it uses it for internal DNS. All right, TCP on here, if you want to go play with it, by all means. I actually finished this, and you can get bidirectional communication going through a firewall with an established connection, right? So it can go both directions now. And then during that established connection, you can modulate the SYN packets from one side, the SYNAC packets from another side for different modulations, right? And get two-directional or bidirectional communication. It doesn't work here because I didn't want to give that to you. But if you want to play with it and get it working, then by all means. Okay. Now, amplitude modulation. We'll just kind of whip through these. I'm not going to recreate the sign for you. Amplitude modulation works great too. In fact, over the Ethernet, it'll just kind of change the size of the packets, right? And so, generally speaking, from now on, anytime I do a red team engagement, I have internal communication and things on the same subnet, I'm absolutely using this every time because there's no detection for it, right? So that's great. But this is what this kind of ends up looking like internally. You can use IP. And then I did ICMP for the example for what we're going to do on the remote end, right? So, and this can go way faster. So that's with amplitude because I have a clear, it's one byte or another. I use the ampersand byte because when that shows up in packets, it does show up quite randomly. If you use just a dot, right, you can just use a period. That's what the null bytes look like when you do packet inspection anyway, because 0, 0 is a dot. So if you just use a dot as the extra byte, it just looks like nothing, right? So that's another option. Okay, so we'll do this. Cool. Again, 30 hops, RSA network, and I can go way faster, right? So that's cool. We'll give it a little second to do the processing. I can go nearly as fast as I want. At some point where you have to like find the tolerance of like retransmissions and like packet drop, right, across the hops, so that's something to worry about. But it goes really, really fast. I can transmit more information. The bigger deal here is that, again, RSA conference network, it just allowed ICMP out, no problem. And for the most part, if you go to most networks, you can like ping Google, because that's generally allowed because it's just used for a lot of stuff to test things, right? It's like a IGMP, IP, whatever it may be. Same thing for IP. If they're doing ICMP inspection, you can do this with IP, just the receiving end has to only be listening for the expected IP on the other side, right? Because you no longer have a port to receive it, so you can't specify the port. And with ICMP, I can specify, hey, it's ICMP, I'm not expecting other packets, go ahead and do this transmission. But with IP, you can do that as well. And generally speaking, firewalls just don't look at IP at all because they're waiting for more data and they're like, I don't know, I guess go ahead and get out, right? So good to you. Okay. So we'll skip to the last bit here when we're looking at the frequency modulation. I'm going to go back to some slides and then we'll talk about it. So I did do a time delay like phase shift, right? That ended up just looking like this. Kind of looks a lot like frequency modulation, just a little bit more unstable, right? So it is an option. It kind of builds in like natural jitter. You can do that. And it's just changing where you're measuring the interval. That's all it really does. So that's fine. Or we can do the phase shift by port number, which was even more stable than using the amplitude modulation by using bytes of data, right? And so we can do that across the board here too. Now doing this with a port requires that you do have more cross-section, but there's still no data inside the packets, right? Cool. And the point here is I'm now going out UDP. I'm going out to 1, 2, 3, 4, 5, 1, 2, 3, 4, 6. Again, allowed out, kind of weird. I mean, I expected it would be. I didn't actually test it, so I'm glad it worked, right? I expected it would be allowed out. UDP is not as locked down as TCP generally is in environments, and so it's a nice way to be able to get out. The problem is it's not generally a bidirectional protocol, right? But you can make it one. And with this kind of transmission, again, even if they're looking for it, when you see like quick traffic and other kinds of UDP traffic, like Netflix is UDP streaming, right? WebSockets end up using UDP. So there's a lot of UDP like noise, and especially when you have UDP with like no data inside the packet, it's gonna be really difficult to detect. Right? So that's why that works too. So there we go. And that transmitted, again, over 30 hops. So we'll pop back into the slide deck and get through the rest of this. Now, there is, in the GitHub, there is one for each one of these. Okay? So there's, for frequency modulation, there's one for every protocol. So it can work, so you can go and test it in your environment. For amplitude modulation, every protocol. And for phase modulation, same thing, okay? So you can go do that inside your environment, see if you can detect it. It's a really great way to figure out what firewall rules are and are not working as well, and you can start to lock that down. For things like Log4j, this is taking it back way more simple, right? For things like Log4j, it required multiple connections back out after the payload was executed for the exploit to actually work. And so one thing they didn't tell you, or like they should have told you, like everyone should have known this immediately, is to stop the exploit from happening while you're trying to figure out whether you had patches or not. You should just shut off the ability for whatever those devices were to talk back out. And it would have completely stopped them from being exploited. That's it. Okay. So cross-site detections, we covered that. Just so you know, Suricata was running with like every rule I could find on that receiving end device, even just now. And when we go look at the alerts, there's nothing. I can go look them again if you want me to prove it, but there's just absolutely nothing in there. In fact, it really didn't like I was curling if config me, right? And this is a good point for just noise. This is just me on the box doing what I was trying to do to understand, like I wanted to show like there's videos in the slide deck that have like, hey, look, it's external IP. That's what I was doing. And then it has some other stuff from Metropolis, like this was just having stuff on the internet, bad stuff happens, right? So someone's trying to get into port 22 already. That's okay. Other than that, absolutely nothing, and it had all the drop rules enabled too. No issues. And then when we go look at the sessions, oh yeah, that's the other part. So what becomes really interesting is now I don't have to worry about any encryption. And one of the primary detections, like things that's tough to do, is like, oh man, if I have an executable or something that's got like reverse shell in it or like shellcode, like those detections are pretty narrowed in. They're like, oh yeah, that's shellcode, nuh-uh, right? That's it. That's got an MZ header. We don't like it, right? Because that's executable. Well now, because none of that is actually inside the packet, I can transmit an executable over the network with 0 detections, right? I don't have to worry about encryption. Awesome. And when we do the phase modulation, it does have the different flow IDs. So you can see every single time it made a new port connection, every single one of them was a different flow ID. So it couldn't even start to do detection on the packets in the first place. Right. Good. And the file I used wasn't just an executable. It was also a known bad malware that I wrote a while ago that leaked out called IronCat malware. That's why all the IronCat stuff, right? There's a family of it. Microsoft has a family. You can look it up. But anyway, that's what I transmitted over the internet. Nothing blocked. I also downloaded it. Nothing blocked. It's fine. Of course, your endpoint stuff, once stuff on the endpoint, that's not the solution. This is network traffic and evasion for network detections, right? Once you're on the endpoint, different story. But good. And so that's where it becomes really interesting is none of these things that are based off that same technology, and the Microsoft EDR uses like a snort-like or a Suricata-like detection when it does have network detection turned on. It'll look for bytes in the packet. You'll even see in the alerts you get, it's bytes in the packet, right? None of that works for this kind of communication. Great. And this breaks all of the phase modulation when we're breaking that session, breaks all the detections for everything else. Cool. All right, so why did I do that, and how are you going to apply it? Well, the big deal is this took me about, I don't know, like I've had the idea for a while, so I've been like working on it mentally. But with ChatGPT, it took me about 2 nights to finish. Okay? So if I can do that in 2 nights, you can bet whatever you hold dear that malware and threat actors are already doing it, especially if it's something that evades all of your detections so easily. So instead, I create it, give it to you, you can go test it, develop detections, and now you are ahead of time prepared for that more advanced threat. That's why we do it. So what you need to do now is use this as a way to go work on your outbound and inbound firewall rules, whatever they may be. I think that's actually the easiest control to implement. Don't worry about detections, just work on your firewall rules. Every environment I've ever gone to work on, really advanced environments, really not advanced environments, all of them have issues with their firewall rules, right? All of them have old firewall rules, and all of them allow some stuff out that they shouldn't, right? And there's easy ways to just shut that down. Okay, so that's one way that's really good, especially when you get down to an individual host. If you don't have control over your firewall, that's okay. Every single device has a local firewall, and you can set that via GPOs. You can set that via like automation for Linux. You can do it however you want to do it. But you should have those rules in place for individual hosts as well. And if you are in a space to have control over that and not the firewall, then that's a great outlet for you to be able to make it where, hey, this web server doesn't need to browse the internet. Things need to browse to it, right? So maybe I just don't allow that until I need to do an update or something. I can go change it, do my update, change it back, right? Okay, so that's the kind of thing that you can work on immediately using these tools, being able to kind of send packets with whatever protocol you want to anywhere you want, have the receiver on the other side, you can see if it made it. That's the idea, right? Now, after that, firewalls are great, but we're still going to be, there's always going to be some way to get around, especially with a tool like this. Now it doesn't matter. I can get around however I want, okay? And you have to be able to have inspection on these packets. You have to actually have visibility into what's happening on your network to do detections, right? Or you just have no idea. And so that's the next step, is make sure that wherever you're sending this, that you have those detections in place. And that sounds simple, but when we start looking at things like just the Ethernet, guarantee you don't have collection of network traffic at every space in your environment where you can see layer 2 communication, because almost no one does, okay? So that's something that you can go figure out and how to implement. Same with the IP, there'll be different segments. There's different tools like Archme versus Suricata, right? That's like an option, right? Archme was made by AOL. Anybody realize they still existed? That's cool, right? So AOL actually manages a bunch of websites. Sorry if you work for AOL and you're in here, my bad. But they manage a bunch of websites, and they created a tool called Archme that does network inspection and session inspection at scale. And so, thousands of deployments, open source, really cool, kind of like the Netflix style stuff, because they're trying to solve a problem that wasn't solved yet. They have a custom sniffer, right? So the tool that does the collection of the packets to shove it to do the analysis, right? It's called a sniffer. Like TCP dump, like NetSniffNG, there's lots of different libraries to do that. Each one of them views packets differently. And so after doing some testing with these, some of them just didn't see some of these packets at all because they're malformed. So whatever technology you use, the enterprise ones, based on one of those technologies, I promise, right? It's just like a nice sticker on top of Suricata, including, I don't know if I went through the slide really quickly, but who works for like a state in the US? Nobody. It's cool. It's a small crowd. It's unlikely. It's fine. Okay, so the DHS, CISA, they give out sensors called Albert Einstein sensors. It depends what phase of the project, or what they call it. It's just Suricata with like 30,000 rules in it. Okay, that's what it is. So if you work in that environment, that's what they're detecting on, and this is the things that you need to test. All right. That being said, 6 months out, there's ways to detect this, but it's computationally expensive. When we're breaking sessions, you now have to write like custom behavioral analysis to look at the behavior of all of the packets at the same time and pull out these signals, right? Because we're recreating signals. It can be done, but it is very computationally expensive to do that in all locations in your network. And so that's going to be the issue with it. But I encourage you over 6 months to find ways to detect it, because there are other ways. The problem now is that we have infinite ways to variate it, right? And so like if you detect based off, oh, if I use amplitude modulation, I use an ampersand, I can look for stuff that's just this many bytes and has an ampersand, right? I can look for Ethernet packets that have no additional data. I can do that kind of stuff. Like those are things that you can do, but it's a cat and mouse game for detecting it. But either way, use the tools, figure out how to detect this stuff, and then you'll identify where threat actors are also doing it. That's it. Questions? Not a single question. That just can't be right. There we go.
So would this kind of technique be kind of more undetectable as if it was, instead of like random nothing traffic, kind of shifting port numbers with normal looking traffic?
Yeah, absolutely. So if you want to be more stealthy, the idea would be, especially with all these options, the idea would be that when you show up in an environment, you say, okay, let me look and see what current traffic is happening, right? And then I'll just blend in with whatever that is, depending on where I want to go, 100%. Yeah, and because you're crafting the packet, you can make it look like a Cisco neighbor discovery packet, but then just modulate it. And if that looks like it's supposed to be normal environment, yeah, who cares? You don't need to put data in it anymore, so you don't really care what protocol it is. Absolutely.
Amazing, and this was an incredible talk.
Oh, thanks, man.
Thank you.
Appreciate it. Yeah.
Hi.
Hey.
Great stuff. Thank you. I'm
Yep.
glad I came to your talk instead of the other ones this morning, even though there's almost no crowd.
That's okay. I did it for me, not for them.
Yeah, sure. I was wondering whether or not, do you happen to be the first one to show this publicly?
As far as I know, yeah.
Okay.
And this is the first time I've shown it
Okay,
publicly.
I thought so. And if that's the case, what would be your assessment whether or not this has been used in the wild already?
Yeah. So I believe I saw a version of this with ICMP using Morse code inside bytes in like a CTF. and that was like 5 years ago. So if that's true, and the TCP option story is true, then this is probably highly likely used in the wild already. But it's going to be cases, like if a threat actor is at this level, they're probably doing a lot of other stuff that make it hard to detect them as well.
All right. Thank you.
Yep.
Really scary.
Yeah.
Thanks for the beautiful presentation. So, can a PCAP, full PCAP capture in the environment can help in this type of detection, or still it will be unable to help?
Yeah, it can absolutely help. The issue is that when you're looking at that traffic, it just looks like all the other traffic, right? The tools that we buy and spend a lot of money on and then put in place to do this kind of detection in the cloud environments, it's even more difficult to get like network taps, quote unquote, but you can do it at the local NIC. But the tools that we use essentially capture the packets and then look at those packets and then compare them with signatures and or weird behavior, right? And so right now, with all of the current stuff I could test, none of that can catch this at all. And I've been working in the detections for a very long time, and knowing how they work, there's not a lot of ability to detect this kind of stuff right now.
Okay, one more query. Like, say ICMP, like you pointed, it is inbound, it is denied. Say, you are browsing a particular server from the internal network.
Yep.
And sometime what it does is that it sends some sort of a ICMP echo replies. Probably then again that with increased MTU, the connection go outside. So that can also be a worry?
Yeah, absolutely. Yeah, so you could, and I maybe misunderstood, but you could essentially use ICMP out and something else back in. You could alternate protocols to transmit information, right? Like ICMP could be 0, and then like HTTPS could be 1, or whatever, like whatever you want to do.
Okay, so
Right.
different type codes you were talking about, 8, 11, and all those.
Yep.
Thank you, appreciate it.
Yeah, absolutely.
So if I understand correctly, all of your techniques, each packet represents a single bit. Is that correct?
Yeah, in this case, yes. When I first started doing the frequency modulation, that wasn't true. It was based off the number of packets sent within a period, right? So it'd be like burst transmission. So one thing that's nifty, frequency modulation, I honestly didn't expect it to be very stable. It was much more stable than I expected over distance. That being true, now you can go look up all these methods and techniques, like Spy in Moscow Station. Has anyone read that? It's a good book. I think it's like free too on Audible. Anyway, Spy in Moscow Station, they kind of cover a bunch of techniques that were used in the 60s with burst transmissions and like high gigahertz transmissions to like evade people who were looking for spies with like different devices. And so now, because we can use frequency transmission, you could apply those same techniques to the way that these communicate, where you do like rapid frequency transmission and stop. And then so you can't tell, it's not like a continuous transmission. And so that would, to do that, you'd have to use multiple packets for 1 bit, right? So it'd be like 3 packets for 1 bit and 4 packets for another, or whatever.
So with one or even potentially fewer bits being represented in
Yep.
a single packet, do you find there must be an upper limit on the amount of data you can exfiltrate or the size
Yeah.
of files that you can transfer, I would imagine?
Yep, absolutely. So I haven't like tried the upper limit, but the executable that I transmitted over the internet for testing was 6.4 megabytes, and it took 2 hours. Yeah,
Okay, thank you.
you're welcome.
Hi, thank you. It's a great novel idea which you have demonstrated today.
Hey, thanks.
So I have a very hypothetical question, but you can actually, based on your experience, try to answer. Whatever you have demonstrated on a real Ethernet or a high-speed network looks very possible. But what about those sporadic networks where the delays or the change in the frequency of the flows could be because of the wide area network or different sets of communications?
Yeah.
So would you like to give some thoughts on that?
Yeah,
Or
absolutely.
did you experience?
So for frequency modulation, that's why I was worried about it. It's because I figured that like if you go 1,000 hops, which I don't know what 1,000 hops would be, but if you do, like you're going up to the satellites, come back down, go around, right, whatever it is. If you're doing 1,000 hops, if that latency was random in between transmissions,
Yep.
it would throw off the frequency. So the interesting part though is like there's tolerance built into it, so you'd have to like increase your hertz, and the like larger hertz you had, the more you could like build in a tolerance to detect those peaks and valleys, right? And so you'd have to figure that out. That's one thing. The other piece of it is it was irrelevant for amplitude modulation as well as phase modulation. So it was latency independent.
So do you see any possibility of false positives or frequency modulation in such cases?
What would you mean false positives?
Like the detection goes up while the actual issue could be a network transmission related problem.
Oh yeah, absolutely.
That's
yeah, and
possible.
that's why it'd be frequency modulation's more fun because if you can make it's going to naturally like blend in with just spurious transmissions and stuff. TCP is a little scary in this case, which is why it's broken in all your Jupyter notebooks. Because like if you just look at your traffic in general, like spurious transmissions happen all the time, stuff's getting dropped, like sequence numbers are weird, but like if it's just pure TCP at that point, being able to hide the signal in an established in and out like bidirectional communication is pretty scary.
Thank you.
Yep.
Hi, great talk by the way.
Thanks.
So I wonder whether you've heard of steganography before.
Yeah, absolutely.
Do you consider this a type of network steganography, one of the types?
We'll call it that now, sure. Yeah. But thanks for coining the term. That's cool.
Actually, it's a very well-known term. So the standard way that they deal with these problems is that they measure all the traffic and then they see like if it's different than the standard deviation, like how different is it from normal traffic. But with Gen AI, it's becoming even more of a problem because you can generate those traffic and let it seem like it's exactly the same thing. So I feel like I'm pessimistic and I feel like there's a lost cause there. You know, there's like
that's why I'm red team.
If you
Yeah. No, I completely agree. I think, like, when I was considering whether to do this in an open forum or not, the thing that I keep coming back to is it's a lost cause whether I did it in an open forum or not. At least now you know about it, right? And then if you're on the defensive side and trying to develop detections, hopefully, if we do, I mean, so legitimately we have AI-ish stuff now, right? And DPUs, whatever. So if we actually do start using that in firewalls, because we had been saying we were doing it for a long time and it wasn't, but we do start using that at like network gates, okay? But we do now have an opportunity to identify signals like this, right? Like at this point, you could probably, like computationally it's gonna like suck right now, but you could probably drop one of these packets in with traffic from a normal network and say, hey, find the sine wave in here to GPT, and it might catch it, right? And so like that being said, like if we can start to do that kind of thing, but in real time as the technology gets better, there's an option there.
Yeah, thank you.
Yep. Any more questions? Cool, I think we're like right on time. Thank you.